Sushruta for NEET is now available on the Google Play Store. Try it out for free.
Hi students, so we continue with our ongoing presentation of um, um, thermodynamics. Um, Last time we looked at the basics of thermodynamics. We looked at the first law of thermodynamics, and then we looked at the ideas around the introduction of the system and the control volume. Then we further looked at its relationship in the context of uh, various types of systems that we consider as part of thermodynamics. Thermodynamics is also, as I explained, studied as in chemistry because they deal with a lot of systems as well in large chemical processes which involve heat, light, heat and chemicals, which then produce, um, which are then recombined to form newer substances or refined in metallurgy, etc. So we already explained that part of it, but then I thought I will take one more attempt to teach this the revise the material that we looked at last time, and then go forward with the new material in thermodynamics. Okay, so let me get going here. All right. So here we are. So as we discussed in thermodynamics, we deal with a system. It is whatever we want to study, may be as simple as a free body or as complex as a power plant, right? We may want to study a quantity of matter contained within a closed, rigid, walled tank, okay? Or we may want to look at a pipeline, etc. So we define a boundary, so the boundary defines the system, and sometimes the material in the system is isolated and we look at it like we would in a closed system. Now, a closed system is known as a control mass, that is, consists of a fixed amount of mass and there is no exchange across the boundary. Okay, so now look at this system boundary, right? In this system boundary, there is no exchange of matter between this and the outside world. So that is a now it the one thing that can exchange is heat and other forms of energy. If even that is not possible, then we say it is a isolated system. That is, the whole system is kept separate and isolated. Now, that is what we do when we do calorimetry, right? We try to build an isolated system in calorimetry to understand the flow of heat, right? While here, in thermodynamics, it's a little bit different. We have large plants which we look at. So now you can have another form which is called an open system or a control volume, as the case where you have only a region of space, but there's air coming in or some form of liquid coming in, something comes in and then something goes out. Okay, so that is a control volume. The most common control volume is the room that is being air conditioned. I'm not talking about the AC itself. Okay? The room that is being air conditioned. The room that is being air conditioned, typically there is air that is, can flow one way or the other. There is air coming in through or air going out, right? So that is in some form, that can be considered, a system, right? So typically, when we look at a um, A steam engine, that is a control volume. They keep adding water. The steam is blows and then it goes away, right? It's not held in place in the steam engine. It goes, it does its work in making the steam engine move, making the wheels of the train move, and then it's gone, right? They go out, right? Or the gas in a IC engine, the air that is brought in, and then the fuel is burnt, and then the fuel is let out of the tailpipe, right? So all these are control volumes. Both mass and energy can cross the boundary of the control volume. So now, typically, what we do in our analysis with thermodynamics is we pick the boundary and then we study that boundary, and then we study the boundary using specific rules. And therefore, we had this two approaches which we called the macroscopic approach and the microscopic approach. Microscopic approach is the statistical approach, and that was also pioneered by Kelvin and Stephen, and then we had this Boltzmann, right? Boltzmann constant, you all know. So they pioneered some of this statistical thermodynamics, which eventually made its way into we looked briefly at black body radiation, sigma a to the power a times t to the power of 4, right? The amount of radiated energy is sigma a t to the power of 4, right? The Stephen Boltzmann law, right? So now, in those kinds of studies, they did a lot of these what is called statistical analysis, but even more so in the context of the micro side, that is the microscopic side of things, that is in the inside of small atoms. So there they did a lot of work using what is called statistical thermodynamics, and you might have all heard of Satyendranath Bose, after whom is famously named a world of what are called boson particles. Today we all hear of the God particle, which is the Higgs boson, right? He was a statistical. He studied statistical thermodynamics, and so there's classical thermodynamics is what we are dealing with here, and classical thermodynamics deals with a few laws, and those laws we'll be looking at, right? So now we also then discuss the three types of processes. Isobaric, typically the word bar means pressure. Isochoric, choric means volume. So iso means constant, baric means pressure, iso is constant, choric means volume. So we have properties such as macroscopic characteristics of the system, by which we describe the system behavior. The state refers to the condition of the system as described by the definite value of property. So now, typically, when a system is in an initial state, it goes through a number of changes, and finally, it returns to that same state. Okay, so we have one property A, another property B, goes to some complicated set of process and comes back to its old state, right? So this is the case when your something is going through a cycle, cyclical behavior, right? Now, in many ways, a lot of things, they undergo some kind of transformation process, then they come back to their original state. For instance, the freon gas in a air conditioner, right? It is liquefied, it becomes vapor, then it is compressed and cooled, and then it becomes liquid again. Okay, so that, and it goes through that process many times inside the air conditioner, even as you are experiencing the effect of that. In an air conditioner, the energy is provided by electricity, right, which then is transformed into compression of the liquid, right, and then the fan is then also exhausts some of the air from inside into, and then supplies cooler into the house, right? And then that kind of circulates in the room, right? So this process, in the freon gas, on the other hand, inside the AC, that undergoes a cyclical process. So now a property is called extensive. Its values the sum of the values of the parts. So if you have an extensive property, just mass, volume, or energy, more is more, right? You use more of it, it becomes more. Intensive properties are properties like specific heat or temperature, which are a single value. There is not, you add more to the same thing, it is still the same value. Temperature is one such thing, still stays the same, right? Then there are specific properties which are intensive also, but which are per unit volume, right? So now so we say that something is in thermodynamic equilibrium, so when it experiences no change in properties when it is isolated from its surroundings. Okay, so in some cases things will be in equilibrium, although there's dynamic action going on. Okay, the amount of there is a flow of heat, there's a flow of maybe even particles moving, air moving inside it, but it is in some kind of equilibrium. Now, equilibrium can be in the form of pressure, if there is no change in pressure at any point, or thermal equilibrium, the temperature is the same throughout the system. Now, reversible process, let us consider the equilibrium of the system as it undergoes a change in state. The moment the weight is removed from the piston, mechanical equilibrium does not exist. As a result, the piston is moved upward until equilibrium is restored. Quasi-equilibrium process is one in which the deviation from thermodynamic equilibrium is infinitesimal, and the state the system passes through during a quasi-equilibrium process may be considered equilibrium state. The quasi-equilibrium process can be viewed as a slow process that allows the system to adjust internally, so the properties do not change any faster than those at other parts. So there is a rate at which things happen. That is a quasi-equilibrium. In the non-quasi-equilibrium process, things happen in a very dynamic, very fast way. So, typically, they therefore they use this dotted line in describing what's going on. So now, here is a closed system, being compressed and then expanded using the piston, right? So here there is the closed system. When you compress it, you're increasing the pressure, and the pressure is increasing, and the corresponding volume decreases. Therefore, you have a PV curve like that. So now, when you do, so how is that achieved? You're doing work on the system, right? So now, work when it is done by the system is positive, which is different from heat. Heat provided to the system is positive. Heat to the system and work by the system are both positive. Work done, on the system is negative, and heat supplied by the system is also negative, right? We already went over that. Now we discussed isobaric. Therefore, work is typically P dV. F ds becomes P dV. And in the case of V constant, there is no work, right? In the case of isothermal process, PV equals nRT. Therefore, PV is a constant. Therefore, P dV will become P1 V1 ln V2 by V1, right? Because you can write it as an integral, as I described, dV by V kind of integral. Similarly, we had a polytropic process where you also have another integral, right? So then we discussed the heat. In the case of heat, there is when there is heat supplied to the system, it is always positive. Heat transfer to the system is positive, while heat transferred by the system to the outside world is negative, right? So temperature distinguishes thermodynamics from other sciences. Right? Temperature is a measure of the hotness or coldness, right? However, sensitive human thus maybe we are not able to gauge it. So we have this this idea of understanding temperature through thermometers, which expand, right? So there is a transfer of energy into the thermometer, and that heats up the mercury typically, and then that expands when there is heat supplied to it, and that is a linear expansion, right? And so Ka dt by dx, right? So we already looked at that, but then the probabilistic model, right? We also discussed this last time with respect to the kinetic theory of gases. This probabilistic model was given by Maxwell Boltzmann. P, the probability of the speed is given by this formula, right? So the probability of the speed is given by this formula. So it will be this much. The probability of the speed is this much. The probability of finding a molecule with speed v at a given temperature is given by this, right? So that's a continuous distribution, right? Maxwell Boltzmann distribution. So it's a probability versus speed curve, right? So now at a given temperature, right? So if the body is at a given temperature, not every molecule will go at the same speed, but there will be a optimal range of speeds that these molecules go to, right? And therefore, we then don't speak of everything moving at the same speed, right? We speak of three speeds. One is the average speed, mean speed. Then you have the most probable speed, right? And then you have the RMS speed, right? So these three are calculated. One is the average speed is 8 RT by pi. The most likely is 2 RT by m, and the RMS is 3 RT by m, square root of 3 RT by m, right? So this is the Maxwell Boltzmann law, right? So the average speed distribution, these are basically integrals that you do, right? So if you do 0 to v f of v, right? So this is, what is that, expected value it's called, right? So when you do the expected value, you get v bar, right? So you do integral v probability dv, then you get the v bar. Similarly, you can get v RMS, which is v minus v bar the whole square. Okay, so v minus v bar the whole square, pv, okay, or square root of that pv, right? And then you can also do the most probable value. It can also be found by differentiating, right? How do you find the most probable? Take the derivative, right? So those are the three ways you find the three values. And then we already looked at this 3 kt over m, and we found that E equals 1 by 3 rho c square. So that is how we introduced last time, right? So today we are going to continue with our discussion of, then we introduced the first law of thermodynamics. If you remember the first law of thermodynamics, it is basically the law of conservation of energy, right? So let me right. So first law of thermodynamics, the law of conservation of energy, so basically, what does it say? That energy can neither be created nor destroyed, it can only be transformed from one form to another. So now, heat, right? So if the quantity of heat supplied to a system, it's retold in the context of thermodynamics using the following law, right? If the quantity of heat supplied to a system, so that makes it positive, is capable of doing work, the quantity of heat absorbed by the system is equal to the sum of the internal energy of the system and the external work done by it. So you supply heat, either it will lead to the system's internal energy going up, U, right? Or it will lead to work being done by the system. Very simple law, follows conservation of energy, right? So dq equals du plus dw. So for each additional piece of heat that you add to the system, it will either do work itself, that will be positive, and then it will lead to du is the energy, internal energy that it gains. So you supply heat, it does work, or its energy increases internally, right? So that is the simple idea. So now we already discussed intensive and extensive, and basically when it comes to a measure of the internal energy, typically temperature is also a measure of the internal energy in addition to PV and T, right? So when we look at the work done, this integral P dV typically, So now if you had the if a system has what are called adiabatic walls, then only um, only mechanical interaction is possible. Adiabatic means the system itself is heat-wise isolated. Only mechanical changes are possible in the walls. Okay. Now, if it is diathermic, then you can supply heat through the system. Now, if it has a porous wall, then the material itself can weave in and out, right? So now, and the classical example of a porous wall is through these membranes that are used in water purification, right? So in water purification, you have a semi-permeable membrane of some sort, and that membrane will push clean water. They put dirty water on one side, clean water on the other side, then they will flush the dirty water into the other side to make clean water, right? So now there is no ideal wall. Most walls are approximations, but then these are all fantastic processes that are so important to everyday life. These why do we spend so much time learning thermodynamics? Because it's so essential to all the things that we do learn, that we do in life. Thermodynamics is a very fundamental science, just like chemistry. That's why chemistry and thermodynamics is a very integral part of chemistry. Thermodynamics itself is a central science, just as chemistry is also a central science. In everything in chemistry, we have thermodynamics, and so you should study thermodynamics very well, particularly if you're going to be in one of these, if you're going to be any kind of engineer, very important field to learn. Okay. So assume that a system is divided into two equal halves in equilibrium, pressure and temperature are unaffected. Okay. So now typically there is no ideal wall. Okay. And so we have different notions of what is called equilibrium, right? And so for instance, PV equals nRT. So if something is in some kind of equilibrium, time doesn't become a player. PV equals nRT, there is no T as in time. The T in PV equals nRT is temperature, right? So now if there are changes, they are infinitesimal, slower than any other characteristic. So if there is a reservoir, which is a closed box, typically we speak of it as having infinite energy capacity. So this is the first law of thermodynamics is what we are looking at, as you know. So when you supply heat, the heat will either when you heat up, say, a gas, the gas will do work, right, in the form of like a steam engine, which makes the pushes the wheels of a train, right, and also increases the internal temperature and internal energy of the associated steam, right? This is the latent heat that it heats up the water from room temperature. Room, of course, the room is very hot, but it heats it even more in that furnace, and then it eventually transmits latent heat, right? So if you have a mass m times latent heat will give you the Q equals ml. Uh, when it converts to steam, typically it will convert to steam at a specific temperature. So that's why you have m times L, how much ever mass times the latent heat of water, right? So that is the Q provided, right? So now what happens to that water, right? That water is going to drive the engine, so that's going to do a dW. But at the same time, also the internal energy of the water goes up. Okay, that's what happens when you supply when you boil water, right? Its internal energy goes up, and so that's why you need to heat it, right? So there's a latent heat transfer. Heat transfer becomes the internal energy. So gases have the particles of a gas move much faster. Therefore, to make that happen, and that reflects internal energy. You already looked at Boltzmann equation, right? So it starts moving much faster at that very high water vapor temperature, right? Water vapor will move much slower at lower temperatures, So at the boiling point moves much faster. That represents the internal energy of the water. So delta Q equals delta U plus delta W. That represents basically the first law of thermodynamics. I supply heat to a system. The system will do both work and its internal energy will go up, right? And the sum of the work and the internal energy will equal the heat supplied. Now, the interactions, so now what do we mean by internal energy, right? Typically, if U is a state function, while Q and W are not state functions. U depends on the initial and final states, right, of the system in question. So now, so so that was the first law of thermodynamics. Okay, there are three laws of thermodynamics. Okay, the third law of thermodynamics is actually not taught typically, but it is also a law that that at 0 Kelvin everything is at rest. Okay, the ideal temperature of 0 Kelvin, right? So now we are at the 300 Kelvin, right? Or 310 Kelvin, somewhere there, 35 degrees centigrade, right? 273.14 plus whatever the degree temperature is, right? That is the Kelvin temperature. At 0 Kelvin, there is no movement at all, right? Now, so so at 0 Kelvin, there is no internal energy, So that is the third law. But now we are going to look at the second law. Okay, so the second law was a very important important law because at that time the internal combustion engine changed the world. In between 1800 and 1900, the internal combustion engine and various other things, they came to modify everything, and the internal combustion then led to coal-based combustion, and led to also power. A power plant is thermal power plants are largely how modern electricity is made. So the efficiency of an ultra-critical thermal power plant is as much about thermodynamics as it is about the way the turbines run. Okay, so so thermodynamics is a fantastic and very important science. It's in your car. It helps power your house, etc. So the second law of thermodynamics is stated as follows. Okay, so the second law of thermodynamics came with the introduction of another term which we call as entropy. We already know this term temperature, T, right? So in addition to T, there is also this thing called entropy, S. right? So we already looked at the various terms. Q, right? Heat, right? W, work. U, internal energy. T, temperature. And now S. Okay, S is called entropy. Now, but the second law of thermodynamics, as with any of the many of the laws, is is stated in also in a very it was found by Kelvin was an Englishman, and Clausius and Planck. So they stated it the following way: no process is possible whose sole result is the absorption of heat from a reservoir and the complete conversion of the heat to work. Okay, so if there is no delta U, right, they are saying that is never possible. I have delta Q equals delta U plus delta W, that you know already, is the law of conservation of energy. That's a very precise law. What they are saying is, but there can be no case when delta U is zero. Okay. Now, so there can never be what is called the. We will introduce this concept of efficiency of a heat engine. Okay? The efficiency of the heat engine is the ratio of the work to the heat supplied. Okay. After all, that's the most important part of the whole game, right? If you can convert all the work, more power to you, literally, right? So, but the second law of thermodynamics tells you that you can't have more power to you. Okay, there's a limitation to the power. Okay, uh, so the alternative way of stating it, right, is just as we stated Newton's first law also in two different ways, or Newton's second law also in two different ways. We are also going to state the second law of thermodynamics in two different ways. No process is possible whose sole result is the transfer of heat from a colder object to a hotter object. Sole result. Okay? There will be some other change as well. Okay? That's what they are saying. Okay? So now they introduce this term entropy. Okay? So entropy is an extensive thermodynamic variable. We already looked at what are the types of variables: intensive and extensive. Right? Entropy is an extensive variable also, just like mass and heat. Right? So given an equilibrium state, right, it has a definite value of entropy, and it is what you call as a state function. So now there's a small amount of heat that is transferred to a system which is at a temperature T, right? The final entropy minus the initial entropy is equal to the integral of the heat transferred by temperature. Okay, so which is it's at a given process, integral delta Q by T is SF minus SI. Now, if this is a in an adiabatic process, the entropy change is zero. Why? Because of the Q, right? Adiabatic process, there's no Q, right? So as a result, the entropy change will be zero. But then the general statement is SF minus SI plus integral delta Q over T. Okay? So now that is the definition of entropy. Entropy is also an extensive, just like volume, mass, and other things. But then it is it is a measure of a variety of now there are different forms of these of other extensive properties that are typically taught as part of thermodynamics, and we are listing these different properties. Okay, the first one is called enthalpy. H. Okay, H is enthalpy. Okay, and then we also have G, which is the Gibbs free energy. Okay? The greater the Gibbs free energy, enthalpy is a measure of the you know is a measure of the heat imparted or the heat capacity or the energy produced by through heat means. Okay, Gibbs free energy represents the part of that that can be provided as free energy to do work. Okay, so that is G. Okay, so these are additional terms that are used. The one is Q minus Ts and the other is E minus Ts. Okay, so Gibbs free energy and enthalpy are H and G respectively. We already discussed S. Typically, S is multiplied by T to produce a term. S is of heat is in joules, as in work, as just like work, right? H and G are also forms of work. They are joules, measured in joules. Now the entropy is joules per Kelvin. Okay, so you typically have T times S, or T times, more specifically, delta S. So that represents the entropy. Now, entropy can be thought of as a measure of the chaos in the system. So now we are going to discuss this what is called the Carnot cycle. So now Carnot cycle, one must understand these various processes that happen. Okay. Now, typically, we looked at this PV diagram before, right? PV equals nRT. We said it's a curve, right? And then we looked at these PV diagrams, right? Similarly, just like that, we now look at what is called a TS diagram, right? Now, just like we had isochoric and isobaric, right? In a TS diagram, the TS diagram is an equivalent of the PV diagram. Okay? A process, remember, S is a state variable, right? So just as P and V, you go from one state to another, right? You go from one TS point to another TS point. Okay? So when you traverse a TS point where there is no S change, right? Where the temperature changes, but there is no S changing, we say it's an isentropic process, a straight line in the TS diagram. That means the temperature changes. The x-axis of the TS diagram it's always y versus x, T versus V, right? When we say it's always y versus x, V is in the x-axis. PV diagram, T is always in the y-axis, right? Similarly, with the TS diagram, T is always in the y-axis. So now, T, if you have a isothermal process, right? If you have an isothermal process in a TS diagram, that will be a horizontal line. Isothermal means temperature. So the temperature stays constant. The entropy alone changes. Okay. If you have an isentropic process, it will be a vertical line. Now, in a TS diagram, what the area under that TS diagram, like T delta S, will give you the net heat exchanged. Okay, so delta Q, because of the integral that we did here, right? Delta Q, T delta S will give you the delta Q. Okay, so T delta S will give you the area under the curve is the net heat exchange. Now, if it's an isothermal process, the entropy changes. Right? Isentropic process, the temperature will change. Okay. So now, we already looked at. Now, let's move on to what is called the Carnot cycle. So, in a Carnot cycle, there is a certain you take a certain closed reservoir, and that closed reservoir, let's assume that it undergoes a cyclic process. The Carnot cycle is a cyclic process, which means that things go from one point to another, to another, to another, and come back to the same point. So it goes through a full cycle, a full circle. Okay, and typically it's not a full circle, rather it's something like this, right? Okay, so think of why is it like this. So let's say you have PV. Remember, PV equals nRT is typically valid. Okay, although that is only for ideal gases, but mostly we say PV equals nRT. So now, if you have PV equals nRT, then P versus V will be a hyperbola. P, so if P is constant, P times V is a constant, therefore it will be a hyperbola. Okay, then next, that is the one part. Okay, then the next part of the cycle is that happens when you have constant T, right? So which are the constant T? One is a constant T, right? The entropy increases, but the temperature stays the same. So that will be a hyperbola. The next one where you go from this one goes from here to there, right? The next one where you go from this point to this point, right, is going to be so this was what? Constant temperature, isothermal. So this is going to be a isentropic process or adiabatic process. So here you're going through a constant S process where the temperature changes. Okay, so adiabatic process has a constant entropy, the temperature changes. Okay, then it goes like this. Now, what can be said in an adiabatic process, right? Now, in an adiabatic process, right, PdV, right? You have PdV, right? Now, PdV is going to be constant. PV is going to be constant. For one constant temperature, PV was constant for part one, right? Here, when you go from here to here, the S is constant. Okay, so if the S is constant, there is no temperature, there's no heat supplied to the system. Okay, so if the S is kept constant, there is no heat supplied. Okay, so the adiabatic process just goes from one point of PV to another point of PV, but without there being any heat transfer. Okay, so now there is no so there is heat supplied here, right? No heat supplied in the adiabatic process. Okay, then there is the third step where the system does work, or in the first case there was heat supply, right? In the first case, the temperature was constant, right? Heat was supplied, right? So now in the second case, no heat was supplied. Now the third case, heat will be provided by the twin system. The system will transfer heat away, right? So there is negative heat supplied. That is, the system will be supplying heat back in step 3. Okay, in step 3, the system is going to be supplying heat back to the environment. Okay, then in step 4, you will have another adiabatic process so that it comes back to its original state. Okay, so these are the 4 steps in a Carnot cycle. Okay, now at the end of the 4 steps, the system goes back to its original state, and some amount of heat has been transferred to it, and some amount of work has been done. The work that has been done is the area under the P versus V curve. Okay, the area in that oblongish shape, right? These are not straight lines. Okay, these are curves. Okay, This one is a hyperbola, right? This one is also some kind of a curve. Okay, the area that is captured inside it is the total work done by this machine, right? The total work done by this machine is the area inside the T versus V curve. And so that is the it represents the work done as part of the Cardinal cycle. Okay, it is now the heat transferred is the area inside the T versus S curve. Okay, so much heat has been added to the system. It is the area inside the T versus S curve. Uh, in this side, it has given heat back, so it's negative, right? And the vertical line says there is no heat transfer, adiabatic process, isolated, right? So the ratio of the areas in the T versus S curve, which is the heat transferred, to the work done in the P versus V curve. The area inside the P versus V curve is the work done. The area in the T versus S curve is the heat supplied. So the ratio of these two areas, which will be more? The area in the T versus S curve will be more. This area will be more than this area. Okay. Why is that? Because of Kelvin statement. No process is possible whose sole result is the absorption of heat from a reservoir and the complete conversion of that heat to work. So there can be no case where the area in the in the P versus V curve in the Cardinal cycle will equal the area in the T versus S curve. Okay. There can be no case. So that is the second law of thermodynamics. The work done will be always less, okay, than the T versus S curve. Okay. So let me take a moment to briefly discuss, what happens. For instance, the most common systems that use, that produce energy are these thermal reactors, which power our power supply, right? Where coal is burnt, or in the West, typically there is also natural gas which is used. Coal is also used in the West. A lot of lignite is burnt in Germany. Bituminous coal is burnt in America. Subbituminous coal is burnt in India and China. Various forms of thermal reactors exist. Okay. Now, in all these reactors, right, the coal produces heat. Okay, that heat is converted first into mechanical energy, then into electrical energy. Okay, so that process of conversion typically has an efficiency about the best that they've achieved is in the low 40s, low to mid 40s. In hotter countries, it is even less. So in India, if you get 40%, you're doing great in a ultra super critical reactor. So and so that is the main theory that goes into this Cardinal cycle. So now I'm going to continue discussing the Cardinal cycle. Okay. Okay. So remember H minus Ts, right? And remember that the area under the T delta S gives you the heat, okay, typically, and P dV gives you the work. Therefore, the ratio of the two areas gives you the efficiency. Okay, so now we will be discussing that efficiency. Okay, so so I'm trying to make thermodynamics a little bit simple for you, so you understand this. You get this basic idea then I kind of, it is typically not taught in this form, but I want you to understand it in these terms. Okay, so now as we said, work done is in different thermodynamic processes. We have the isothermal process, where temperature remains fixed, therefore the internal energy doesn't change. Therefore, you have PV equals nRT, so P and V alone change the hyperbola, right? We discussed that. Now PV equals a constant, right? Then we discuss the for the isothermal process. Then we discuss the isochoric process, etc. Right? When we discuss the adiabatic process, where there is no heat transfer, right? So now PV equals a constant, right? So now in an isothermal process, because PV is a constant, you write P as nRT by V. And then because T is a constant in isothermal process, when you do the integral PdV, you end up with nRT ln V2 by V1. dV by V, when you integrate, it will become ln V. And ln V, you will end up with ln V2 minus ln V1, and ln V2 minus ln V1 will become ln V2 by V1. So you have expansion, right? So you have work done is positive. You have expansion, the work done is positive. Remember, when the system does work, it is positive, right? So if V2 is greater than V1, there is work done by the system is positive, right? Now, if there's contraction, there's work done on the system, then it is negative, right? So now if you have a isochoric process, V is kept fixed, and if V is kept fixed, then there is no work done. There's no work done. Heat is absorbed or released. There's just a change in internal energy. Whatever heat is absorbed is just goes to increase the temperature or time pressure. Okay. When temperature and pressure increase, the internal energy alone increases. Okay. So now we therefore end up with these two largely, in a adiabatic process, there is no Q. Okay, when there is no Q, you have what is called an adiabatic process, and in an adiabatic process, you have this gamma that comes into play, and PV to the power of gamma equals a constant. Okay, now this gamma is Cp by Cv, is a ratio of the specific heats. Cp minus Cv equals R, and Cp by Cv is gamma. Okay, PV to the power of gamma equals constant in an adiabatic process. Okay, and there is no delta Q there. Okay, so we already looked at that, right? This is the horizontal vertical lines in the T versus S, right? The vertical lines, the T versus S, there's no heat transfer. T delta S is the heat transfer, right? So now, when you do that, dou P by dou V equals minus Ci by Vi square, right? And here dou P by dou V is gamma C by V r to the power of r to the power of gamma plus 1, right? Therefore, you end up with gamma P naught by V naught, and therefore that is the P naught by V naught is the slope of the isotherm. Okay, so so if you have what is an isotherm? Isotherm is when you have a given P and V. Okay, when for a given PV product, right? That is the that is the value. Now the slope is the where you are in the curve. The slope will keep changing, right? So that is the point that they are making in the case of so so here dou P by dou Vi is minus P naught over V naught. Here you have they introduce this gamma, right? Therefore now the adiabatic process, work done is more, okay, in an adiabatic process. Okay, work in the expansion process, work done so when is there expansion and when is there contraction, right? So let's look at expansion and contraction, right? So right, so when you are here and here, your expansion. Step 1, step 2, right? Expansion. Step 3, step 4, contraction. Okay. So now, during the expansion processes, work done in the isothermal process is more. Why is that? That's obvious, right? It's like this. While this one is much steeper. Remember, the area under the P versus V curve is the work done, right? So here there is more work done, and again here there is adiabatic work done is more. Okay, so that is the point there. Okay, so now with isobaric processes, P is kept constant, right? So when P is kept constant, what is the work done? T times V2 minus V1, and that is what? NR times T2 minus T1. So that is for isobaric, right? So your P versus V curve is what? Straight line, horizontal line, right? Now when you expand, it goes from low V to high V, and when you contract, it goes from high V to low V. Very simple, right? Now, in a when we discuss reversibility, right? So this is the basic thing with respect to second law of thermodynamics. You go through a process like that in a car, say in a Carnot engine. You cannot go through a process where all the energy you gave can completely be removed completely, okay? Or all the energy you gave became work. You will never have that case. That is the basic idea. And so there will only be a portion that gets grabbed and gets converted into energy, and that ratio defines the of the work done and the heat transferred, right? The work will be a submultiple of the heat, and the ratio of the work done by the heat transfer will be a small value, like 30%, 40%, like that. Okay, so that ratio gives you the efficiency of the engine. Okay, the working goes in a closed cycle. There are multiple thermodynamic processes. So you have hot reservoir and the heat absorbed from the hot reservoir, and then heat released to the cold reservoir. Work done is Q1 minus Q2 in a reversible heat engine. Okay, but really there is no real reversible heat engine, as you all have heard, right? So if you had a reversible heat engine, Q1 minus Q2 is the total Q supplied is Q1, right? Then some of that is supplied back to the second system, Q2. So Q1 minus Q2 is hopefully converted into work, right? Q1 minus Q2 divided by Q1 will give you the effective efficiency. You will never have efficiency of Q1 minus Q2 by Q1 will give you the work done divided by heat absorbed. Will give you the total energy. Will give you the total efficiency. So now a refrigerator is a hot reservoir and a cold reservoir, right? Hot reservoir has a temperature T1, cold reservoir has a temperature T2, right? Now heat is absorbed from the cold reservoir and then released to the hot reservoir, and the work is done on the system. Okay, therefore the heat absorbed divided by the work done gives you the coefficient of performance of the refrigerator. Now, I've more or less reached the end of the hour, so I'm going to halt for today, and we will discuss things further next week. All right, so let's move on for today, and then we will continue our discussion with closing out thermodynamics, and then we'll start something new next week. But for now, please understand this, how this Newton's second law of thermodynamics fits into the equation, and how the Carnot engine operates. And the area of in the P versus V is the work, and the area in the T versus S is the heat, and the ratio gives you the efficiency. So we will discuss more about this in the context of the refrigerator and other systems in the next class. And this is roughly how thermodynamics is taught from, say, a mechanical side, but then there is also thermodynamics that is always taught as part of the um, uh, you know um, kinetic theory, and thermodynamics is also taught in chemistry and is extremely important in chemistry. So please also pay great attention to Tiwariji's lectures so that you learn that material also very well, very good. If we have more quality engineers in India, and also these kind of cyclical processes also happen in your body. There also you will have all kinds of cycle, Krebs cycle, this cycle, that cycle. So understanding some of these ideas in the context of physics will also help you segue and understand these things in a body. Human body is also a system, and therefore I advise you to pay careful attention to thermodynamics and understand these processes as well. All right. So with that, I'm going to stop today's lecture. We will continue our discussion next class.